In this video, we're going to look at quantifying and calculating the electrostatic and gravitational force. Before we do that, let's review a couple concepts. If you have a single electron or a single proton, it is helpful to know the charge of that charged particle. We call this the elementary charge. The magnitude of the elementary charge is 1.6 times 10 to the negative 19th coulombs. Coulomb is our unit of charge. This is a very, very small amount of charge, but it is a single electron or a single proton, so that makes sense. Also, you need to know that if you have two charged objects, they're going to interact with a force between them. Opposite charges, like positive and negative, will attract, while like charges, like positive, positive, or negative, negative, will repel each other with a force. Now we can calculate that force. There is an equation called Coulomb's law. Coulomb's law is Fe is equal to K times Q1, Q2 over R2 or R squared. Now we can define each of these things. The electrostatic force is represented here by Fe. In the IB Physics data booklet, it actually shows up just as F. So right now I'm using this to isolate and identify that. This is a force. We're going to use units of newtons for any force. Object 1 charge is Q1. Charge is measured in coulombs. Object 2 is Q2, also in coulombs. And then the separation distance, we're going to use the letter R to represent that. That is going to be measured in meters. Now, one of the challenging parts of using Coulomb's law is placing everything in these units. Typically, you won't see things in coulombs. We'll have to convert that. Typically, we won't see distances in meters. We'll have to convert that. Now, there are a couple other things that you'll notice here. There is a K in here. We didn't define K on the last slide. K is a constant. We call this Coulomb's constant. It is 8.99 times 10 to the ninth newtons times square meters divided by Coulomb squared. Now, this is a crazy unit. It's not a unit that we typically see. So let's prove that this is the unit. If I take my equation and I solve it for K, I get something like this. K is equal to FR squared divided by Q1 times Q2. Now I can use dimensional analysis and plug in units for this. F is newtons, R is meters, then each of the Q's is coulombs. So I've got newtons square meters divided by coulombs times coulombs. I can simplify that and it turns into newtons times square meters divided by coulombs squared, or coulombs to the minus 2. That matches this unit. So that is the unit required in this constant, so that when I substitute everything onto the right, I will get newtons out to equal my force. This equation and this constant are both in the IB Physics data booklet, so you'll be able to access those things. Sign is important when we talk about this equation. It is possible in this equation to get either a positive or a negative value because charge could be positive or negative. It turns out that if both of them are negative, you'll multiply them together to get a positive, or if both of them are positive, you'll get a positive. Positive times positive is positive. So that means if you have a positive force coming out of this, both Q1 and Q2 are the same sign. So that means they will repel. Positive and positive or negative and negative will interact by repelling. If you get a negative force out of this, it means that one of them was negative, but the other one was positive. If you have a positive and a negative, they are opposite signs, so they will be attracting. So just so you know, a positive force indicates that you're repelling, negative is attracting. But typically, we only report the magnitude of the force, so the positive negative usually goes away in the end, but that is what it means in this equation. All right, like I mentioned, typically in this equation, you will not be seeing coulombs and meters, and you have to convert it into that. So if I have 7 microcoulombs, I find micro is 10 to the minus 6th. So in coulombs, it's 7 times 10 to the minus 6 coulombs. If I have 14 centimeters, centi is 10 to the minus 2. 14 times 10 to the minus 2 ends up being 0.14 meters. 14 centimeters is a little bit less, well, less than 1 meter, 0.14. All right, I can take that and solve a problem with it. A small quark with an excess charge of 7 microcoulombs is placed 14 centimeters from another quark, which carries a charge of minus 3.2 microcoulombs. What is the magnitude of the electric force between the quarks? This is my Coulomb's law equation. I know what K is, and I know what all of these charges and distances are. I can convert that. Micro is 10 to the minus 6th, and then centimeters 10 to the minus 2. And I plug everything in. 8.99 times 10 to the ninth times 7 times 10 to the minus 6 times negative 3.2 times 10 to the minus 6 divided by 0.14 squared. Now, a couple things to identify on here. It is very important to remember this square. That's commonly missed when you type it into a calculator. Also, if your calculator has the E button, the E notation is really useful when we're doing an equation like this that has a ton of scientific notation. I would type this in as 8.99 E9 times 7e negative 6 times negative 3.2 e negative 6 divided by 0.14 squared. When you do all of that, you'll get an electric force, this electrostatic force of negative 10.3. That negative, again, means attracting. If I look back at my charges, I had a positive and a negative. I already know that opposites should attract, so that negative confirms that. All right. There's another equation that you should know that is very, very similar. Here we've got the universal law of gravitation. Fg is equal to g times m1, m2 over r squared. You'll notice this looks very similar to what we just saw. Here, this force, Fg or F, is in newtons. Object 1 mass is m1, that's kilograms. Object 2 is the same idea in kilograms. And the separation distance, just like we saw, is r in meters. Now, this equation has a different constant. Before, for Coulomb's law, we had K, Coulomb's constant. This, we have capital G, or big G. Big G is a universal gravitational constant. It is 6.67 times 10 to the minus 11th newtons square meters per kilogram squared. Notice this equation looks very similar to Coulomb's constant. We've swapped out Coulomb's and put in kilograms instead. But everything else we could prove this in the same way, do some dimensional analysis and see that that is the unit that comes out of the equation. This equation, as well as this constant, are also in the IB Physics data booklet, so you have access to all of those things. You just need to know where to find them. All right, gravity, as well as electrostatic force, is an equal and opposite kind of force. If you are skydiving, you obviously are experiencing a force of gravity pulling you down, but it turns out that gravity is a two-way street. Two objects with mass are required for gravity to act, and that gravity is equal and opposite. Both objects experience the same force pulling them toward each other, and we only really think of it as a force on the skydiver because the skydiver has less mass, so more motion happens because of that. But the same, if I was skydiving, the same 735 newtons pulling me down would be pulling up on the Earth, but the Earth being so massive wouldn't really budge in that force. So, another factor that's important to identify here in Newton's law of gravitation is that technically the law states that it's a gravitational force between 2 point masses, and Earth isn't a point mass. There's volume and mass existing in that volume. So, Newton also has a separate theorem called the shell theorem that states that a spherically symmetrical shell of mass m acts as if all the mass was at the center. So, we can imagine that Earth is basically just a bunch of spherical shells, and we're just going to pretend that all the mass is at the center of the Earth. Why that matters for us here is that we have to have a distance in this. The distance is basically center to center. So if you're talking about the Earth to the moon or the Earth to me, we are talking about the centers to each other. So if I'm touching the Earth, my distance is not zero. The distance is the distance of my center to the Earth's center, which is basically the radius of the Earth, because in the end, like my radius is going to be very, very small in that calculation. So here is an example problem. Determine the force of gravitational attraction between the Earth, which has a mass of 5.98 times 10 to the 24th kilograms, and a 70 kilogram physics student. If the student is on an airplane 40,000 feet above the Earth's surface, that would place the student at a distance of 6.39 times 10 to the 6th meters from the Earth's center. So that radius of the Earth has already been factored in here. We can just plug everything in. Again, big G has a constant value that we can look up, 6.67 times 10 to the negative 11th, times the mass of the Earth times the mass of the student, divided by the distance squared. This one's extra important to make sure you're not forgetting that square, because when you have scientific notation, it's often easy to forget that you have to do another thing as well. If I do all of this, I will find that the force of gravity on that student is 684 newtons. We have another way of calculating the force of gravity, mass times gravity, but that 9.8 is only good for the very surface of the Earth. We will see how that G might change at different distances later on when we get into field strength. So one of the things that you should have already noticed is that these equations, they look very similar to each other. They're the exact same inverse square law and inverse square relationship. The only differences are we've swapped out the constant. So in electrostatic force, we have K, which is Coulomb's constant, and gravitational force is big G, which is the gravitational constant. The other big thing is what is the property of the material that impacts the force. For electrostatic force, is how much charge the material has, or the object. We call it Q1 and Q2. And for gravitational force, it is how much mass the object has. So M1 and M2. But other than that, it's the exact same format of an equation to give you a force that is equal and opposite. So both objects are going to experience that same force, either attracting or repelling. All right, there is one other feature that is built into Coulomb's constant that shows up in the IB physics data booklet that I want you to be aware of, but we're not going to talk about in great detail. Coulomb's constant is sometimes expanded to the form of K is equal to 1 over 4 pi epsilon sub 0. So epsilon naught is the permittivity of free space in the vacuum, and that is a constant um, in a vacuum. It is, and if you plug this number into this equation, you will get K of 8.99 times 10 to the ninth Newton meter squared per Coulomb squared. The exact same thing that we saw in the data booklet. Um, this shows up in the data booklet. Right next to Coulomb's law, you'll see this K is equal to 1 over 4 pi epsilon. And you'll see that that epsilon naught permittivity of free space shows up in the fundamental constants. Now, I do not recommend plugging this in to calculate K and then use K. Just use the K that's already in the data booklet. Use that 8.99 times 10 to the ninth. Where this might factor in is if you are not in an environment that you can approximate as a dry vacuum situation, free space. Um, so if you are changing it, air is slightly higher relative permittivity. Paper, concrete, rubber, water, all of those different materials would change that permittivity, which would then potentially change K, which would then potentially change your electrostatic force. But all of those things you might be able to work yourself into how those different things might interact. We're not going to look at that in detail in this video. So the takeaways here, you should be able to calculate electrostatic force using Coulomb's law, and then calculate gravitational force using the universal law of gravitation. Essentially the same relationship, just new properties built in. You should also be able to describe the impact of separation distance on how electrostatic and gravitational force act. The larger the distance, the smaller the force. And it actually decreases very quickly because it's an inverse square law. So you square that distance. So doubling the distance actually decreases the force by a factor of 4.